Hello to everybody and welcome to this video. Today I would like to show you how to do nonlinear backlink of a beam using Abaqus. So to do so, the geometry used will be a 3D beam which will be modeled with shell elements. Material will be steel with these properties. Abaqus units are Newton millimeters, tons and seconds. The loading will be an axial compressive force, and the target of this analysis will be to get critical backlink load, the stresses from the backlink load, and we need to determine what is the failure mode. That is, if the beam will fail under backlink or just under the compressive load. So to do nonlinear backlink, we need to follow workflow. So first of all, we need to create a linear backlink job. So we need to build a model, create a start buckle step, and we need to edit the keywords of the model. We need to add this line to get to do the nonlinear. This will help us doing the nonlinear backlink analysis. So from linear backlink, we will extract the eigenvalue, which will be the critical linear backlink load, and the backlink mode. So we input that into the nonlinear backlink together with editing the linear backlink load. We need to change the step to a static Rix step, considering non-linear geometry. And we need to edit the keywords in the non-linear backlink step in order to add the imperfection file. So how the mode is contributing to the final results in order to get stresses and the load proportionality factor, and therefore the nonlinear backlink load. So those three will be the outputs from the nonlinear backlink analysis. So we'll get the load proportionality factor, with that we'll get the nonlinear backlink load, and therefore the stress values on the geometry. So I need to say as well, non-symmetry, non-linear backlink, we can't use the symmetry. So although this beam will be symmetric, but we cannot use that. It's not recommendable. And this is the introduction to this exercise. So we will move on into Abaqus platform. So here in Abaqus, first thing we need to do, as always, is set the work directory. Okay. And now we need to create, in this case, import the CAD geometry. So go to File, Import, Part. So we need to change the file to CAD part because it's CATIA geometry. There is, yeah. So there you go. So we need to set the property. We will start creating the steel material properties. Elastic will be, this is megapascals and 0.3 Poisson's ratio. Okay. We need to create a section. Section 1 will be shell, homogeneous. Okay. The thickness value will be 20 millimeters. Material steel. Okay. And now we will create the property, assigning the section created before. So done. Select the section. This is shell offset is important. In this case, will be middle surface. Okay. If we would like to see the how the thickness is rendered, we need to go to part display options and go to shell thickness. Apply. Okay. So here we can see our original surface is this line in the middle. So half of the thickness goes inside and half of the thickness go outside. So okay, we can remove this render view. It's not necessary. So yeah, now quickly go to assembly, create an assembly. This case is easy because we only have one instance. Okay. Next we go to step, create a step, will be linear step. In this case we need to go to linear perturbation, Baku, continue. Okay, so the number of eigenvalues we will only need one. The first mode is the only important we want to extract, but if you need 2, 3, 4, 10 modes, you can add it here. In vectors, if per iterations, normally it is twice the number of eigenvalues requested. So in this case 2, and maximum number of iterations will be 1000. So yeah, that's enough. Okay, so quickly we go to interaction, and now we need to create a couple of points midway between 2 points, and now we need to create one at the bottom, at the top, and one at the bottom. So this is the top, and this is the bottom. With this we will create a reference point, and another one here. Okay, so I would like to create the mesh right now. So go to mesh, global seeds, global seeds. I think 15 will be fine. Yep. Okay. Select the elements. So I will use quadratic elements, S8R, reduced integration. Okay. And mesh. So the mesh is created. So what I would like to do is just create 2 sets. Wait. So create top will be node based. Continue. I will select the top edge. Be careful not selecting the middle node, as this is, all the elements are quadratic elements. All of them have a node between the middle of these 2 nodes. So this is the top, so let's create the bottom. Will be node based. Okay. Okay. So quickly go to interaction. So let's create constraint. This will be the top. Rigid body. Okay. So let's select the tie. And now from sets, we select the top. And in point, we'll select the reference point 2, the top one. Okay. And now we'll do the same with the bottom. So let's create the bottom. Rigid body, continue. Tie, select the set bottom. And the point, reference point at the bottom. Okay. While we have created this reference point and all we have created a constraint of all the nodes on the edge. So the reason why is because we are going to define boundary condition at the bottom and top, and the loading at the top. So referencing this reference point. so that's why. So the load will create at the top, so will be a concentrated force. And as we already don't know the compressive force, the critical backlink load, what we are going to do is just click here, reference point, done, and the load will be -1. So when we get the eigenvalue at the end of the linear backlink analysis, the critical load will be multiplied by one, so the eigenvalue multiplied by 1, so that's why we use 1. Okay, so yeah, this is created, so it's here. So now we are going to create the boundary condition. So first will be the top. Okay, so displacement rotation, and we will remove z and next displacements. Okay, and we'll create the bottom one. Yeah, displacement rotation, and I will select, well, the reference point, bottom, and we will remove all the translations and the rotation in Y direction. Okay. Okay. So the model related to the linear backlink is almost finished. So at this point I will rename it, call it linear. Okay. I will copy it because the non-linear backlink will be very similar to this model. Okay. And now it's selected non-linear. Be careful, we need to go back to linear, double click, and I will right click on linear and edit keywords. So we need to add a line at the end, just almost at the end, call node file. Okay, so this will import the displacement values for the non-linear analysis, backlink analysis. Okay, and now we need to go to job, create job. We'll call it linear again, linear, select the linear model. Okay, we can use multiple processors. Okay, and submit. So this will take a few minutes, so we'll pause the video and we'll be back later. Well, the model is completed, the run is completed, so let's go to results. And here, what we need from here is just to check if the mode shape is what we wanted. This is what we wanted. And the eigenvalue. Okay, so let's write down the eigenvalue, and with this we will modify the non-linear model. So let's go to, well, let's animate the mode just in case we can. I think with the scale factor, I don't know, that's fine. Okay, looks fine to me. To model, well, let's go to step, select non-linear, double click, and let's replace the, well, rename the step, will be non-linear, and replaced by static rigs. Continue, let's activate nonlinear geometry. 1000 maximum number of increments, 0.01 arc length increments, 1 as maximum. Okay, so let's go to load manager, edit. We'll change the unit force by 5.6, 10 to 6, sorry, this, sorry. Okay, now what we need to do is just go to the model, right click, edit keywords, and just before the step, so this is the step, so let's create a new line and start imperfection, comma, file equal to linear step equal 1. So let's add the first mode, and here this value is 1/10 of, oh sorry, so the thickness is 20, so 2.0, 1/10 of the thickness, and okay, looks fine. So now the model is completed, so let's run it. Nonlinear, 2 processors, okay, and submit. So here we need to pay attention to monitor. So here the arc length will be increasing every iteration. So we need to check that when the increase is lower than in the previous iteration, we need to stop, to kill the analysis, because this step RIX will be applying gradually the critical load. So we need to check when this load will be reducing. So we can check it by going, we have the first iteration here done, so we can go to results and check ODB history output. Sorry, oh, there is no values now, so we need more data values, but we can check the load proportionality factor, and when this is decreasing against the arc length, we can kill the simulation and check the results. So I'm going to pause the video, and I'll be back later when I see we can kill the job. I will do it to show you. Here I'm back again, so we can see here all the iterations. We need to just check when the time incrementation is negative, so that means we can kill the process. Yes, so it would in this step on never stop, so unless we do it. It's finished, so let's go to results. Here we need to go first. I will hide the mesh. Okay, we need to go first to XY data, ODB history output, and check the load proportionality factor. So let's plot it. Okay, so here is how it has been applied, force, and here should be a maximum load proportionality factor. So to check this, we need to go to here, XY data, right click, edit, and there will be a maximum. the maximum is, in our case, well, I will say this value. Just copy. Let's go to here. Our load proportionality factor will be this value. I will put it here. So yeah, this value. The nonlinear backlink load will be the load we defined in the load manager for the nonlinear model. Let's go to load. So this is the value of the linear. So the nonlinear backlink load will be this value multiplied by the load proportionality factor, and this will give us a value of 5.46. This is the value in newtons. Okay, so we have the nonlinear backlink load now, and we need to check. What we need to do is just check the stress value at that step increment. So I will close this. Need to go to job, results. Let's check the deformation. A bit more. I will give 100. Well, yeah, the thing is the time step is not very high, so I will just write 20, and let's go to the correct time increment. How we can check that? Can go to RF. This will give us the reaction force at the bottom, and the reaction force should be equal to the nonlinear backlink load calculated. So let's see. Yeah, so the value is this one. Yeah, this one. So 5.46. Sorry. Yeah, that's it. So spot on. We can increase a little bit the deformation scale. So this is how the brace is, deforms, distorted. So let's check the von Mises stress. It will be very high. Let's check where the location is. So the maximum stress will be here. It's very high, far higher than the yield stress. So the stress value is, well, is megapascals, and this stress value is much higher than the yield stress. So the targets are critical backlink load, we got it, stress from backlink load, have it, and determination of failure mode. Well, as the stress due to the backlink load is much higher than the yield stress, we can conclude that it will fail by compressive force stress before than backlink. So backlink is less important here in this exercise than the load, than just the elastic criteria. Okay, so I think that's all. Thank you very much for watching this video. Please don't forget to subscribe and like, and see you later.